Welcome back. In the previous main lecture, we introduced the non-inverting operational amplifier, and we claimed that the input resistance of a non-operational amplifier is very large. In this video lecture, we're going to discuss how we can prove that. So let's begin. Firstly, let's redraw our non-inverting operational amplifier. We still have negative feedback with R1 and R2. Our output, that's R2. But for the non-inverting operational amplifier, we apply our input voltage over here. So that's VI for V input. Now, to get the input resistance, we always apply a test source with voltage VT for test, and we need to determine what is the current flowing because of that test voltage. Once we have that, we can determine the input resistance is equal to our test voltage divided by our test current. And we're going to see that Ri is a very large value. Okay, so Vt we already have a value for, that's just the voltage, but we need to determine what is It. Okay, so where can this test current go? The only place it can go is into that terminal. But what do we know about terminals? They're the terminals of operational amplifier. That current I2 is always equal to 0 because of if you just look at the operational amplifier on its own, it has a high input resistance. So that high input resistance of the operational amplifier causes no current to flow. We're interested in this whole configuration. What is its input resistance? Okay, but in this case, we'll see that both of them are very high. So that means if I2 is equal to 0, It is also equal to 0. So I can say It is equal to I2, and that is equal to 0. And that's one of the properties of our operational amplifier. So to determine Ri, we have Vt, whatever that test voltage is, divided by 0. Whenever we divide by 0, that leads to an infinity. So our input resistance for this whole non-inverting operational amplifier configuration is also very, very high value. In the ideal case, we'd like that to go to infinity. Okay, let's have a look at the special case of the non-inverting operational amplifier, which we'll call the voltage follower or the buffer. Okay, so that is section 9.4.2. It's called a voltage follower because it doesn't amplify the voltage, it simply follows the voltage, also called a buffer. Okay, and initially it looks like a bit of a useless amplifier, but there is a very valuable use for it. Okay, so there is still feedback being applied, but the feedback is directly from the output to the inverting terminal, and there's no resistances. Okay, so how do we analyze this? Well, we still have our properties of the operational amplifier, which we can use. So we can say that the inverting terminal is always equal to the non-inverting terminal whenever we have feedback, and we do have feedback. We know that the non-inverting terminal is connected to VI, and we know that the inverting terminal is connected to Vout. Okay, so we can equate Vout to Vi. Vout is equal to Vi. And if we want to calculate the gain of that, that's just the output voltage divided by the input voltage. And the output voltage is equal to the input voltage. So this will simply give us a gain of 1. So that means whatever comes in at the input will be placed directly on the output. We call this unity gain. Unity gain. Okay, so like I said, initially this seems like a fairly useless circuit, but this circuit separates things on, from its input to its output. Because of its high input resistance over here, it's as if this input is completely disconnected from the output. So whatever is connected before it and whatever is connected after it, we can analyze separately. Okay, so let's have a look at the microphone and speaker example that we had previously in the course and see how using this buffer can help us to more efficiently transfer power between the microphone and the speaker. Okay, so we had a microphone recording something, and we said its voltage Vs was equal to 1 volts. Because of the way it's mechanically built, it has an internal resistance, and we can't do anything about that. So it's 1 kilo ohms of internal resistance. And if you connect that directly to the speaker, we said the speaker has a resistance of around 8 ohms. So for this speaker, it will only receive a partial amount of the voltage of the microphone. So we calculated that using voltage division between that resistance and that resistance. So that is RL multiplied by Vs divided by RL plus Rs. And we calculated the value as 7,936 millivolts, which you'll agree with me is a very small value. If we calculate the power that's transmitted from the microphone to the speaker, we get that value by squaring the voltage divided by the resistance, and that gives us 7,87 microwatts, which is, once again, a very small value. We last time calculated what the power in Rs was, and we saw that most of the power goes to Rs and very little to the speaker. So now we can use the buffer to separate, to split the circuit in two over here. We're going to use the buffer to separate the microphone assembly from the speaker. And we'll see, without any amplification, it delivers the power more efficiently from the microphone to the speaker. Okay, so we're going to use a voltage follower in there. Let's draw that circuit. So we have our microphone. We have its resistance, Rs, connected to the non-inverting terminal of our operational amplifier. We have the voltage follower configuration, direct feedback. And this port over here will now be connected to our speaker. This is our output voltage. So you can see efficiently we have cut the microphone part, put it on the one side, and cut out the speaker part and put it on the other side. Okay, let's calculate what the voltages are in this case. So our output voltage is equal to the voltage across our load. So our load voltage is equal to our output voltage. But remember that for the voltage follower, this is also equal to our input voltage. Our input voltage is the one over here. So once we have an equation for our input voltage, then we can say what the amount of voltage on our load will be. Okay, so how do we get this input voltage? We can determine that input voltage by starting off with Vs and subtracting the voltage drop caused by if there were current flowing in here. So our input voltage is equal to the voltage of the microphone minus I times Rs. But we know that for a voltage follower, no current can flow into the operational amplifier over here. That's one of the properties of the operational amplifier. So that current will simply be equal to 0. So that's Vs minus 0. And that simply is Vs. So now we can say our input voltage is equal to Vs. So that means our load voltage, the voltage across the speaker, is equal to our voltage on the microphone. So V load is equal to Vs, and we said that this is 1 volt. Okay? And if we calculate the power coming from this 1 volt now, so the power delivered to the load is equal to voltage on the load divided by the resistance of the load, and that is 1 squared divided by 8 ohms is the resistance of the load, and that gives us 0.125 microwatts, which you'll agree with me is much, much larger than 7.87 microwatts. Sorry, this is 0.125 watts, not microwatts, which is almost 1,000 times larger than what we had without the buffer circuit. So the voltage follower allows effective transfer of voltage and therefore also power. And that's what we use the voltage follower for. Thank you very much.